Good day, lighters. Welcome to the Graceful Light channel. My name is Bongani and I'm gonna be your facilitator for more sessions that are to come to this session. If you are still new in the channel, welcome. You're still right on time. Subscribe and hit that notification button so that whenever we upload new videos, you can also be notified. We also have our WhatsApp number, which is 065 545 3217. We are still saying that a candle loses nothing by lighting another candle, and that's why we would like to thank the lighters that viewed, subscribe and comment and send us questions on our WhatsApp number. We would like to thank you, lighters, for giving us such a light. Welcome. Today's session is gonna be about continuing on our last session that we did. On our last session, we had questions that were not answered, like in your delta configurations, whereby we said our V line is equal to our V phase, and then our I line is equal to the square root 3 I phase. And then there was question that where does the square root of 3 comes from? So today's session will be about that. We'll be addressing that. We will be answering that where was the square root of 3 comes from. We will prove where is it coming from. So I hope you like that, guys. You will enjoy, you stay tuned. We also left here behind me in the board a question the last time for the letters that they can do it on their own. We did receive some questions or the answers on our WhatsApp number, which I repeat again, it was 065 545 3217. We did receive some answers. We replied to those that were wrong. So today we will be doing the question and the answers as a collective. As we are lighters, we will be doing that. And our last session, it will be about where do we apply these calculations. I can see we are doing calculation in real life environment. Where do we apply them? That's also what we'll be looking at today. So I hope you lighters will enjoy. You stay with me, you stay tuned up until to the last session of the session for today. Please subscribe, please comment. Don't forget to comment, lighters, please comment, and also send us the WhatsApp on our 065 545 3217. So we will be doing the answers of the last question now. Thank you, lighters, stay tuned. This was the question we were talking about that was left on the board the last time we were doing a YouTube video. So let's go together through the question and we will try and resolve the question. The statement here was saying that a 3.3 kV transformer, a 3.3 kV to 380 kV transformer, delta star connected, delivers 20 kilowatts to a certain load at a power factor of 0.9 lagging. So we will need to draw down. Remember on the last sessions we were drawing down before we then answer the questions. So now we will draw the information and populate the information down. It says here that it is a delta star transformer. So we'll be drawing our delta on our primary and our star on our secondary. So it's a delta that is our red line, white line and our blue line. Remember, we are showing the primary side with capital letters. Now we go and draw our secondary side, which is the star. Our star is having a neutral. That's your red line, your white line, and your blue line. So we are done drawing the vector group that was stated in the statement there. So we'll need to populate the information down in our drawing that we get from the statement. It says that it is a 3.3 kV. So that means on our primary side it's a 3.3 kV, and then on our secondary side it's a 380 kV. But remember, we said previously that if it is not stated, we assume that it's our line voltage. Therefore, the voltage on this side, our V line to line voltage on this side, it is 3.3 kV. And then we have our red phase, which is our phase impedance. We have our white phase, and then we have our blue phase. And then on this side, our line voltage, it's either you can draw it between any of the phases here. So now I'm going to be drawing it between our red and white line. So it will be between our red and white line, of which it is 380 volts. And then it says that the transformer delivers 20 kilowatts to a certain load. Then it means here there's a load that is connected to the transformer, and the transformer is supplying this load with 20 kilowatt, and then at a power factor of 0.9 lagging. Remember, our power factor is cos phi. Cos phi is equal to 0.9. So I think we've drawn all the information that was given in the statement. Now we'll have to go through the questions, or we will need to populate all the other information, then we go through the questions. You lighters, you need to know that from our previous session that in a delta, our V line in a delta, it is equal to V phase, and in a delta, our I line is equal to the square root 3 of I phase. This part here will also be proving it, where does the square root of 3 comes from. In today's session and the next session that we'll be doing now, we will be showing you lighters where does the square root of 3 comes from. And then in a star, we know that our IL is equal to I phase, and then our line voltage is equal to the square root 3 our phase voltage. Those were the things that we did in our last session. So if you don't know about them, please go and view the video, the first video that we've uploaded. You will see how did we come about to say that our V line is equal to V phase. Please go back to the first video so that you can see that. And then we also have formulas here of the transformer, which is V1 over V2 is equal to your I2 over I1, which is equal to your N1 over your N2. Those are the formulas that we are using in transformer applications. We also have other formulas that we are using, which is P is equal to 3 VI cos phi. Please note here, there is two equations of the active power. There is also another equation which is saying P is equal to the square root 3 VI cos phi. So when do we use these formulas? This one, you use it whenever you are using phase values. And then this one, you are using it whenever you use line values. So please note of that. I think there will be a question that will be applying both of them, so that the lighters, they can see what's the difference. When do you use P is equal to 3 VI cos phi, or when do we use the formula of P is equal to the square root of 3 VI cos phi. And the last equation that we have is that our apparent power is equal to the square root 3 VI, and then we use line values here. So we've populated all the information that was in the statement, and what do we know in terms of the delta and the star configuration. Now let's go to the questions and see what are they looking. So the first question here, it says that we need to determine the primary phase voltage. So the primary phase voltage, it says that we need to determine this here. We need to determine this here, the voltage across the phase. So the primary phase voltage. So we will then need to answer that question. So your number one, if we are looking here on the information here, the primary side is our delta configuration, and we know in the delta configuration that our V line is equal to our V phase. Therefore, we can go, we know that it is a delta configuration, and we look at the relationship between our phase quantities and the line quantities in terms of the voltage. Therefore, the relationship between our line quantities and the phase quantities in terms of the voltage in a delta, we know that our V line is equal to the square root of 3. We do have our V line here, which is 3.3 kV. Therefore, V line is 3.3 kV. We are looking for V phase. So we can see here that our V phase here, therefore, our V phase is equal to 3.3 kV. So that was the first question, and we've answered it. So we can go and draw it down here that our V phase, it is 3.3 kV. So then let's go to the next question. The next question, it wants us to determine the secondary phase voltage. The secondary phase voltage. And if we are looking at the secondary side, we have our star configuration. So we will need to check what is the relationship between our line quantities and phase quantities in terms of the voltage. We can see here that in a star configuration, which is our secondary side, that our V line is equal to the square root 3 V phase. So we go there for number 2. In a star configuration, our V line is equal to the square root 3 of V phase. Therefore, if we are looking here, we do have our V line, which is 380. It's 380. And then we are looking for our secondary V phase. The P here doesn't represent primary. The P in this case, it represents the phase voltage. Please note that. Don't mistake it with primary voltage. This P here is for the phase voltage in your secondary. That's why in this drawing here we went on our secondary side. Therefore, V phase, it will be equal to your 380 divided by the square root of 3. Let's calculate together, lighters, and see if we'll have the same answer. It's 380 divided by the square root of 3. Therefore, our V phase here, it will be 219.393 volts. I'm using a 3 decimal on after the comma. You can also use 2 or 1. It depends on you. What do you want to achieve? But when you are using 3 decimal numbers, it almost gives you the correct answer. So you can leave it to 1 decimal number or to 2 decimal number. Therefore, we'll go and write our V phase here on the secondary. Remember, I said that V phase, it is the voltage that is measured. If we are looking here on the delta, it is measured across the phase impedance. So even here, we'll go and look for the voltage that is measured across the phase impedance. So if we are looking here, our V phase will be here, which is, it is measured across the phase impedance. Therefore, it is measured between your red line and your neutral line. Therefore, our V phase in this case, it will be 219.393 volts. So that's our V phase. That's the answer of question number 2. Now we will need to go to question number 3. Question number 3, it says that the secondary phase current that you are looking for. So they are looking for this current that is flowing through our phase in the secondary side, of which in this case the secondary side is our delta. We know that in a star configuration, that our I line is equal to I phase. Please remember that. In a star configuration, our I line is equal to I phase because this is the secondary side of the transformer. Now let's go and apply the transformer formulas so that we can see if we can get the phase voltages. Now, number 3. So if we can look here, we have the voltage, but we don't have the current. Even on this side, we don't have the current, whereby we can use this formula here, that is our V1 over V2 is equal to I2 over I1. We don't have those voltages, but we can see here that the transformer delivers 20 kilowatts. Therefore, we can use the formula of the kilowatts on the secondary side. So, which is P is equal to 3 VI cos phi. So, we are using this formula. Remember, I said here, if we are using this formula, then you use your phase values. If you are using this formula here, that's the difference between these two formulas. If you are using this formula here, you use your line quantities. We will apply both of them so that we can see if we can get the same answers. So let's go here. We have our actual power here, which is 20 kilowatts. 3. Now the voltage, because of I'm using phase voltage here in question number 2, this value here, it was the value of the phase voltage. So I'm using the phase voltage because this formula here is when you are using the phase values. Therefore, I'm going to be using the phase voltage, which is 219.393. We multiply by, that's what we are looking for on the secondary, our I, and then we multiply it by the power factor of 0.9. So let's see what will be the value of current. I find the value of secondary phase current to be 3.33.763 amps. That's the value of the secondary current, which is this current here that is flowing through our phase here. Is 33.763. So someone might say that, okay, what if I use the other formula? Will I get the same value as the one that I use? And the answer is yes, you will get the same value as the one that you use here. But the difference is that when you are using the other formula, please know that use the line values, not the phase values. Therefore, let's calculate using the one for line values. So your P here is 20 kilowatts is equal to the square root 3. Now we are using the line values on the secondary side, of which the secondary side is our star configuration. So the line value for voltage on our secondary side is your 380. So we multiply by 380. We are looking for the current multiplied by 0.9. Let's see what is the value of I line. Remember, is line quantities, and the question here is looking for phase quantities. Please remember that. Therefore, let's calculate what will be the value of our line current. The value I have for line current, it is 33,763 amps. So you can see that whenever you use your phase quantities and your line quantities, you have the same answers. But in this case, this doesn't mean that this is the phase current. You have to prove that this is the phase current. Therefore, how do you prove it? Because here it is a line current. How do you prove it? You go and check in your star configuration that your IL is equal to your I phase. You then write it down. Therefore, in our star configuration, our IL is equal to I phase. And then you substitute the value of IL, which is 33,763. That's your I phase. This is where we then compare this formula and this formula, that our I phase is the same value. So when you are using this one, you use your line quantities. When you are using this one, you use your phase quantities. I hope that is clear with you, lighters. Now let's go to the next question, which is question number 4. Question number 4, it says primary line current. Can you hear the difference? Primary line current. So we are looking for a current that is flowing here. Remember here, we just proved that our line current here is equal to your phase current. Therefore here, even here, you can see that your line current here as well, it is equal to 33,763. So now we will be looking for the value of the primary line current. Then we can use transformer formulas here. We can use the transformer formulas. We have our V1 line, V2 line, which is 380, and we have our I2, which is 33. Therefore, we are looking for our I1 here. Therefore, in this case, question number 4, we can use our transformer formulas. V1 over V2 is equal to I2 over I1, which is our V1. 1 in this case, it represents your primary. 2, it represents your secondary. Your primary and secondary values, they can either be line values or phase values. In this case, we are using line values. So let's go and look. Our V1, it is 3.3. And then our V2, it is 380 volts. Our I2 is 33,763, and we are looking for the value of I1. Then we do cross multiplication here. Then we will have I1 as multiplied by 3.3 equal to 380 multiplied by 33,763. Therefore, the value of I1, let's check what will be the value of I1. The value of I1, which is our line current, and that's what we are looking for, is the line current. It will be 3,887,888 amps. That's the value of our line current. So let's go and draw it in our board here. The value of line current, it is 3,888 amps. And then let's jump to the next question. The next question, it says that the rating of the transformer in kVA. So in this case, they are telling us they are looking for your apparent power. So we look here, this is question number 5. So the rating of the transformer. The rating of the transformer, it's either you can get it in your secondary side, or you can get it in your primary side. So we will use both of them in this case to check if we'll get the same rating. For now, we'll be using our primary side, which is S is equal to the square root of 3 VI. And then it will be your square root of 3 multiplied by your V, your line quantity on the primary. It is 3.3 times 10 to the power 3. And then your line quantity on your primary in terms of current, it is 3,888 amps. Therefore, the answer for this case, it will be your square root of 3 multiplied by 3.3 multiplied by 3.3 kV multiplied by 3.888 amps. And then your value for your rating of the transformer in this case, it will be 2.223 kVA. Now let us see if we're using the secondary side, if we will be getting the same value as the primary side. Remember I said when they are looking for the rating of the transformer, it doesn't matter if you are using your primary side or your secondary side, but you don't swap the values that you get in your secondary, you swap them in your primary. You use only the values of secondary for secondary, you use the values of primary for primary. So now let us look what will happen. Will they be the same if we are using the secondary values? Now we are using here, let me say S1, which means this one here, it represents our primary. This case here, I'll say S2, which means it will represent our secondary. Square root of 3 VI. Our secondary voltage, there it is 380. And then our secondary current, it is 33,763. Let's calculate and see what will be the value of our apparent power in the secondary side of the transformer. So my apparent power, my value that I have here, it is 222,222 kVA. You can see that here the answers are the same. I know that here I said 223, here I said 222. Remember when I was talking about the issue of decimals in the issue of decimals after the comma. So that's what I was talking about. When I was talking about the issue of decimals after the comma, that's why now I'm having 2 here and 3. It's an issue of decimals. So let's go to the next question. The next question, it wants a tens ratio of the transformer, your N1 and your N2. How do you get your N1 and your N2? You use the information that you have here. It's either you have your voltage or you have the current. So we'll use both and check if we get the same ratio, voltage, the tens ratio of the transformer. Let's see now. We have our V1, we have our V2. That's the tens ratio. On V1, it is 3.3 kV, and your V2, it is 380 volts. Therefore, the tens ratio, you ask, how many times does 380 goes into 3.3 kV, and how many times does 380 goes into 380? So let's see, how many times does 380 goes into 3.3 kV? It goes there 8.684 times, and 380 to 380, it goes there 1 time. Therefore our N1 in this case, is equal to 8.684, and then our N2 is equal to 1. We can check that by using the current values and check if we will have the same answers. Therefore, if we use the current values, it's our I2 is equal to I1. Our I2 is 33,763, and then our I1 is 3.888. Now again we do the same thing. How many times does 3.888 goes into 33.763? And then how many times does 3.88 goes to 3.888? So let's check for that. Here it goes to 8.684 and it goes once. We can see here that it doesn't matter if you use your voltage quantities or your current quantities. It just needs an understanding that what are they looking for when they are looking for the tens ratio. So it's either you use your voltage quantities or you use your current quantities. I think we came to the end of this exercise here. I hope you lighters you enjoyed. So we've came to the end of this exercise here. So we will be doing the next exercise that was sent by the lighters on our WhatsApp number, which was 065 545 3217. If you enjoyed the session, lighters, please comment if you enjoyed the session. Comment. If you have other questions, also send us on our WhatsApp number. Now we'll be doing the next question that the lighter sent on our WhatsApp number. We will write it on the board and then we'll try to resolve it. We hope you lighter that you've sent the question, you'll get clarity today, you'll stay happy. So please stay tuned while we will be doing the next question. Thank you, lighters. Hi, lighters. The producer advised me that we give a chance to the lighters as well, because this is a two-way program. So we need to give the lighters a chance as well to do the exercise on the board here. So the producer asked me that I give the lighters the chance to do it on their own, then we can do the exercise together again next time when we have a session. So I agree with the producer, because we will need to get the feedback from you lighters so that you can see if you understand. So I'm gonna be reading now the question here on the board, and then after that we'll leave it to the lighters. Please grab your pen and your paper so that you can write the question on the board. So let me read the question on the board. It says that a 400 kVA 2.2 kV to 400 three-phase transformer is a star delta connected. Please calculate the primary phase voltage, the secondary phase voltage, the transformer ratio, the primary line current, the primary phase current, the secondary line current, and the power delivered on full load if the power factor is 0.75 lagging. And they specifically ask that the lighters, they must express their answers in kilowatts. So please lighters, write down the question here, note it and write it down. We will be doing this question on our next session as it was proposed by the producer. But now next time I'll be doing the exercise that we said we will be doing, the one of proving in a delta configuration that why are we saying that our I line is equal to the square root of 3 I phase. We will be doing that. You don't need to do that. We just need to give you confidence that it is like that. So we'll be doing that on the board. So please stay tuned. Stay with me, lighters. Now, lighters, we are about to prove in a delta configuration. Why are we saying in a delta configuration that our IL is equal to the square root of 3 I phase? So we are about to prove that. We promised the lighters that we will come back, we will prove them. This exercise that I'm about to do, lighters, is you don't need to do it. This is to prove to you that in a delta configuration, our IL is equal to the square root 3 of I phase. I just want to show the lighters where does the square root of 3 comes from. So now we are about to do that. Let's do it together, lighters. I hope you'll enjoy the process. I'm going to the board now. So if lighters, you can remember, we were talking about the delta configuration. That in a delta, we said that our VL is equal to V phase, and then our IL is equal to the square root of 3 of I phase. That's what we said. Now I just want to bring that, we see where is it coming from. I'm sure most of the lighters are asking themselves, why the square root of 3? Why not the other number? Where does the square root of 3 comes from? So we are about to prove that today. We are about to prove that with this exercise. I don't think in any exam papers or in any field work that you are doing, you have to prove this. So now let's go and do it together, lighters. This is your red line, your white line, and your blue line. And we assume that our phase rotation, because this is a AC supply, there will be a phase rotation. We assume that it is anti-clockwise. Therefore, you have your red phase here, red phase impedance, and then you have your blue phase impedance, and then you have your white phase impedance. So when we were proving in the last session, if you didn't see the previous session that we did, lighters, please go back to our YouTube channel, look at the basics of transformer, the first episode that we did. We were showing these things, but in that episode we didn't explain the square root of 3. So today we are explaining that. So in our previous session, we said that our line voltage, it is the voltage that is measured between two lines. Therefore, in this case, we will be choosing our red and the white line. So this will be our V line, that we measure it between two lines, that is red and white line. And then our V phase is the voltage that is measured across the phase impedance. Therefore, this is where we measure V phase. So if you can see where we measure the V phase, we still measure it between your R line and your white line. Therefore, that's why we are saying that in a delta, our V line is equal to our V phase, because we measure them across the same points. So that's why we are saying that in a delta, our V line is equal to our V phase. So now we'll be doing the currents. We'll be checking the relationship between your line current and your phase current. And why are we saying the square root of 3? So let's go and check, where do we measure our line current? Our line current, we measure it in the line. Therefore, this case, we'll name this current here I line current red, because it is in the red line. And then the current that is flowing in your red phase impedance, it will be our I red phase. And then there will be a current that is flowing into your blue phase impedance. Therefore, we call it our I blue phase. And the current that is flowing into your white phase impedance, then we call that our I white phase. Now we need to look at the relationship between the line current and the phase current. So if you can see here, there's an anode here. we can see that there is a current that is coming to this one, to this anode here, and the current going to that anode, and then the other one is going out of the anode. So in Kirchhoff's law, let us just draw that. This is what I see there. So there's a current that is going out here, current that is coming, current that is coming. Therefore here we have our ILR, and then here we have our IBP, and then here we have our I red phase. So this is an anode. If you apply Kirchhoff's law, the current one, then you will notice that the sum of what is the Kirchhoff's current law says? It says that the sum of currents that are going into an anode is equal to the sum of currents that are going out of an anode. That's what the Kirchhoff's law says. So let's see if we do this in an equation, then it will be your I red phase is equal to your I red line plus your I blue phase. This is only in terms of magnitude. We know that because of this is an AC circuit, there is also phase angles that are involved. Therefore, we'll name these phasors. Once we then say these are phasors, we then need to draw the phasor diagram for this equation here. But this equation as well, you can also represent it like this. Your ILR is equal to your I red phase minus your I blue phase. And then your I red line is equal to your I red phase plus, in brackets, minus I blue phase. We can also express it in this way. So now we will need to draw the phasor diagram for this to check the relationship between our line current and the phase current. So now if we draw the phasor diagram, in the phasor diagram we always make a reference with our red phase. Therefore, the red phase is the reference I red phase. And you know then the current that is lagging is your I white phase. And then the current that is leading, your red phase, is your I blue phase. That is just the phasor diagram. So now we need to apply this equation in this phasor diagram. So the opposite of your blue phase, it will be in this direction. Your blue phase minus, the minus sign, it will be in this direction. So here we will have minus I blue phase. And then what we know about this, if we can try to explain this states that ILR is the resultant of your I red phase plus minus I blue phase. Therefore, your ILR, it is the resultant of your I red phase and your I blue phase. So now if we look very carefully, if we add this line here and this line here, remember, lighters, is that I'm trying to establish a relationship between our phase current and line current, our phase current and our line current. So now I'm just closing this and I name this point A, B, C, D. So I'm having something like a square here that says A, B, C, D. In terms of engineering, we are then calling it a quadrilateral. So if I was using correct measurements here in the board to draw, you would have noticed that this quadrilateral, which is A, B, C, D, it is a rhombus, because I will show you now why it is a rhombus. Therefore, let me write it. Quadrilateral A, B, C, D is a rhombus. So now, like us, you have to go back to your engineering knowledge that you studied before and try to check what are the characteristics of a rhombus. So the characteristics of a rhombus are that the diagonals in a rhombus, it means the lines in a rhombus, are perpendicular to each other and they bisect each other. So in a rhombus, diagonals, it means this line here, which is here, and the other line that we can draw here to there. They are perpendicular to each other. Therefore, we will show that with a 90 degrees. This is 90 degrees, 90 degrees, 90 degrees, 90 degrees. Therefore, it means that the diagonals, the lines in a rhombus, they are perpendicular to each other. Therefore, in this case, we can then say that your AC is perpendicular to BD. And then it also says that they bisect each other. So we can name this point here, point E, and then when they bisect each other, they divide each other in half. So if we are looking here along this line on our line current, you will notice that your AC is equal to 2AE in this line, because this line is the sum of this line and this line. That's why it is 2AE. Remember that this is our line current and this is our phase current, and we are applying engineering terms and knowledge to establish the relationship between our line current and our phase current. Now, if we are looking here at this point here, you will notice that point A, D, E, and it's going back to A, is a right angle triangle. This point here, point A to D, D to E, E to A, it's a right angle triangle because we have a 90 degrees here. So it is an angle that looks like this. Then we have those two lines there, and then we have one line here. And you have your 90 degrees here at point E, that's your point A, that's your point D. So I've taken out this triangle here, put it here so that you can understand the triangle that I'm talking about. So from our knowledge about this in trigonometry functions, we know that the angle here is 60 degrees, the angle here is 30 degrees, here we have the square root of 3, here we have 2, and then we have 1. So I'm going to take this triangle here and put it back there. I was taking it out of here so that you lighters, you can see. Therefore, if I'm taking it back, I'm having my 90 here, I'm having my 60 here, I'm having my 30 here, I'm having the square root of 3 here, and then I'm having 2 here, and then I'm having 1 that side. Now in this triangle again, I'm trying to check the relationship between my phase current and my line current. So if I then use your angle 60, looking at the angle 60 and checking the relationship between my phase current and the line current, you will notice that if I'm looking at an angle of 60, that AE, this point, is opposite to 60. So that is the line that is along my line current. That's why I'm using it in this triangle. And then AD is the hypotenuse to 60. So we know of this. Once we say opposite over the hypotenuse, then we are using sine, and we reference it to 60, which is what is opposite is your AE, and what is the hypotenuse is your AD. We can then represent your sine 60. You can use your calculators like us and try and see. This is the other way that we can represent sine 60 by using the same triangle. Sine 60, it is the square root of 3, which is opposite over hypotenuse. So it's opposite over hypotenuse. So if you can take your calculator and show that it is in degrees, you press sine 60, it will give you a value. If you can then take your square root of 3 divided by 2, it will give you the same value as your sine 60. So it is the same as if we are representing it like this. Now we can do cross multiplication here. You will have your 2AE is equal to the square root of 3AD. Your 2AE is equal to the square root of 3AD. And you are making your AE the subject of the formula. Therefore, AE is equal to the square root of 3 over 2 multiplied by AD. So we can then take this. We can then take this AE and substitute it in this formula here, lighters. In this formula that we had here, that was saying that our AC is equal to AE, with 2AE, which was in our line current. So we substitute AE to this formula here. Therefore, we'll have a formula like this. AC is equal to 2AE. Now we substitute your AE, it will be AC is equal to 2 in brackets square root of 3 over 2 multiplied by AD. Then your 2 and this 2, they cancel. We are left with AC is equal to the square root of 3 multiplied by AD. So if you go back to our phasor diagram, you will notice that your AC, it is your ILR is equal to the square root of 3. Your AD, it is I red phase. So this is where the square root of 3 comes from, lighters, when you do this. Now I hope lighters are like, this is where it is coming from. I like the aha part, but you don't have to do this. We're trying to prove to the lighters where is it coming from. If you can see, lighters, that we only did with red to white phase. So the lighters can try and do the relationship when you are looking at your white line and your blue line. I'm definitely sure that your phasor diagram will not look like mine. Maybe this thing, it will fall to that side or it will fall to that side. Just try it, lighters. You don't have to do it. I don't think there's a question paper that is asking you to prove the square root of 3. But this was the indication of where the square root of 3 comes from. And why are we saying that our IL is equal to the square root of 3 I phasor? I think, lighters, now we've came to the end of the session, and we also promised the lighters that we will be checking where do we apply these calculations in terms of real life. Because of time, lighters, I will put that in our next session. Please stay tuned, subscribe, comment, also send us questions, or you can send us comments, compliments on our WhatsApp number, which is 065 505 3217. I hope you enjoyed the session, lighters. Hope to see you back next time. Thank you. Ciao.